Here I'm going to briefly describe how we use the NIST WebBook, which is a really valuable resource, a lot of data for thermodynamics. Here I'm going to look at calculating enthalpy and entropy as a function of temperature. So let's go ahead and look at the WebBook by clicking this link. And chemistry WebBook, what we want to do now, we're going to look for a search by name, and I'm going to put in here methane. And I hit return, and it brings up quite a lot of data. What we're interested in is the gas phase thermochemical data. So you'll see heats of formation and from multiple sources, but the values are pretty similar. And likewise, heats of combustion, entropy. And what we're interested in now is, let's go down, this heat capacity equation. And we'll talk more about this, but it's in terms of temperature divided by 1,000. But it's the equation for heat capacity, equation for enthalpy, an equation for entropy. It also then gives the values of the parameters. So the heat capacity over one temperature range, 298 to 1300, has certain parameters. From 1300 to 6000 are different parameters. And so we'll talk about how we would use those. So I've copied some of these values. So let's go back and look at those and look at how we use this information from the WebBook. So there's a couple important things to point out here. The 0 indicates standard state, 1 bar. We're always calculating a difference in enthalpy, so we calculate the difference between the condition temperature we're at and the enthalpy at 298. So when we do an integration, we do it starting at 298. So the interesting thing about the WebBook is this gives an equation for enthalpy, and it shows A, B, C, D, E from integration, and it has these two additional parameters. These account for the fact that we don't have to substitute in the limits. We don't have to evaluate at 298 limit, for example, because that's all done by the WebBook, and it's incorporated into these parameters F and H, and this certainly makes life a lot easier. The other thing to point out is the temperature in these equations is Kelvin divided by 1,000, and since heat capacity is joules per mole, you would expect then when we have the same A, B, C, D, and E for enthalpy, it would also be joules per mole. But because the integration, and we integrate respect to this temperature, we need to end up multiplying the answer by 1,000 because we really should integrate respect to Kelvin temperature. And so that's taken care of by the fact that enthalpies are in kilojoules per mole, even though these heat capacity parameters have joules. On the other hand, for entropy, the calculation is in joules per mole. But likewise, there's this parameter G that accounts for these limits. So let's just briefly describe what those limits are. But the idea is we can calculate enthalpy independent of which temperature range just by substituting in the appropriate parameter. So if I'm at 800 Kelvin, then I can substitute 800 divided by 1,000 into this enthalpy equation, and I would use these parameters. If I'm at 2000 Kelvin, I would use these parameters. And again, the WebBook values for F and H, which you notice are different for the two temperature ranges, accounts for this. And I'll show you just briefly how it accounts for that. So if we're in the temperature range between 298 and 1300, then the enthalpy at some temperature, standard conditions, minus enthalpy at 298. Remember, we don't have absolute values for enthalpy. We always are looking at difference. It's just this integration, 298 to temperature, heat capacity dt. But what we're going to write to that, because we want to use these values, is we integrate respect to this lowercase t. So that 0.298 lowercase t, the heat capacity that I show here, and now dt, which means I should multiply this by 1,000, and I would get enthalpy in the correct units of joules. And then what we've done is that's incorporated into the calculations in the WebBook. So if you use this equation, you'll get an answer in kilojoules because it's taken into account. And then what this integration looks like, so you should note that I'm using A A1, B1, C1, etc., because that corresponds to the parameters in this first column of numbers, right? Because if we're at a temperature, and that's what we're assuming, we're at a temperature between 298 and 1300, this is how we do the calculation. And then, of course, we substitute in, do the integration, substitute in the limits. Okay, so I've done the integration, I've substituted in the two limits. Now, what the WebBook does for you, it calculates this term, and this term is equal to F1 minus H. So this is F1 minus H1. So it does that for you. It puts in the appropriate parameters, and this certainly makes then the calculation much easier to get enthalpy. If the temperature is above so let's look at that table again. If the temperature is above 1300 Kelvin, so we have to use the second parameters. Again, we just substitute into this equation here, and the F and H values, which are different now in this temperature range, account for the calculation of the limits and for the other integration, as I'll show you in a second. So let's make sure to point out here that calculation I showed you so far is if the temperature is between 298 and 1300 Kelvin. Now let's look at the case where the temperature is greater than 1300 Kelvin. Again, I'm going to pause and write down the equation. So because we're above 1300, we first have to integrate from 298 to 1300 using the parameters from the first set of numbers, the A1, B1, that are only appropriate between 298 and 1300. And then we integrate from 1300 to our temperature of interest using the parameters from the second column of numbers in the heat capacity table, A2, B2, etc. And we can do this integration. Of course, we can do both integration. We effectively have done this integration for this first integral. And let's just write down the values then for the second integral. Now you'll note that I listed the integrals perhaps the reverse of when I did the integration for this term. I first wrote the evaluation of 1300, that's right, a minus sign. And then I wrote the plus sign for the valuation of t. And the reason I did that is because now we're going to look at all these terms together, and they're equal to F2 minus H2 in the table. So instead of having to do this calculation each time we wanted to do a determination of enthalpy, the WebBook has done that for you. It's listed in the table. It's calculated, and that's where the F2 and the H2 values combined come from. So that means the calculation for enthalpy is certainly much easier because we're just substituting in this plus the F2 minus H2. So the calculations for entropy are very similar. Keep in mind, final result for enthalpy, kilojoules per mole, but entropy, it's joules per mole Kelvin.